Hello, my name is Alex. Today I will talk about the scene I have selected, the materials I have produced, and how they work, and finally I will showcase all of them in the scene. I choose Cyberpunk as the main theme. In my perspective, Cyberpunk society is defined by capitalism, inequality, and huge income difference. Visual aspect of the cities depends on the area. Average and poor areas consist mostly of neon holograms, however the rich parts are shifted towards realistic things. But what differentiates being rich or being poor, I came up with an answer for myself. It is casino. You never know when you will be lucky and become a rich society member, or the opposite, becoming homeless after unlucky all in on the green. Initially, I started work by creating a mood board and collecting references images. Most of them were collected from a platform such as ArtStation, DeviantArt, Pinterest. However, some references were also taken from OpenArt, AI-generated images, and videos. Initially, I came up with the following ideas for materials: a digital terrarium, bottles with reappearing brand logos, hologram chips, art paintings, and expensive flooring materials such as velvet. When it comes to rich places in the digitalized world, the most expensive items are the physical ones. So when I thought about what materials might be for decorative purposes, velvet was an interesting possibility. To create a velvet material, I set up a UV with a custom offset and scaling in case we want to have more density in our material instances. Then we get our height map and save it to a separate variable that will be used in the future. Same we do with the ambient occlusion, except we want to apply a contrast to get smaller details. To control that, we introduce a parameter called AO contrast. In general, for a base color, we take two colors and our height map. Because our background is mostly black, our primary color can be utilized as a background. To make a more realistic look and make it possible to reuse the material in different scenes, we may also control the metallic, specular, and roughness levels. It will help to achieve new velvet feeling by improving the glossiness, or otherwise making it feel a bit older by increasing the roughness. Of course, to make velvet more aesthetically pleasing, we do use a normal map. Additionally, to ensure the visuals, I have changed the shading model to the cloth, which added a few pins such as fuzz color and cloth. Fuzz color allows you to add colors to your material when light passes through your materials, and cloth represent how strong that fuzz will be. To get them, I use pre-existing function fuzzy shading, which emulates the shading of a velvet, which is perfect for this case. Possible instances might change color, glossiness, and AO levels to have different density velvet with multiple colors in different scenarios. Next is the dissolving material as a decal packer. Initially, I wanted to implement dissolving bottle brands. However, due to the nature of the decals and depth buffers, they cannot be applied to transparent objects. So instead, I adapted this material for casino logos and area labels such as lobby, bar, and roulette. First comes moving noise texture using panner and 2-speed parameters. It is responsible for determining the dissolve effect, direction, and visuals. Next comes the dissolve amount, where we control the speed of dissolving by a new parameter. Then we normalize the output of a cosine from 0 to 1. Then we use that value and map it using a curve that can be specified by the designer. All the curves should be added to the atlas first. Finally, we pass the color, width of dissolve, noise texture, and amount of dissolve to the function. It adds the width and amount together, then it maps noise texture values to either 0 or 1 based on the previously calculated sum. The result of this operation will be an opacity mask we return. We apply the color and return it as additional output. Finally, to show only the needed part of the logo or text, we apply the mask to the decal by multiplying the label texture with the opacity mask to make it more aesthetically pleasing. With such exposed parameters, it is possible to use this material for any text, label, or logo we want to dissolve and set any curve for specifying the visibility. Following the idea of casino, the most common item associated with it is the chips. Because of a cyberpunk theme, I decided to make them as holograms. In my mind, even the chips are holograms. With the technology of the future, it will be possible to interact with the holograms realistically. To implement a hologram, all we need is a hologram mask texture, which we do move by customizable speeds. However, there are different types of holograms. They might be either overlapping or just moving in any direction. To make it possible to customize, I introduced noise frequency. When set to a number any other than 1, will create the overlapping effect. To control how many lines an hologram player sees, I also added a density variable, which we multiply with a frequency, then multiply with UV, which we finally pass to a panner node to move the texture with the previously provided speed. Next is to create chip itself. To maximize reusability, I split it into two parts, inner and outer, and they do follow the same idea. For the inner part, we do have an inner mask to know the bounds of the logo. By specifying this mask, it is possible to introduce two colors for the logo itself and the background of the logo. To merge them, I use a linear interpolation with inverse logo as alpha mask. Almost the same idea applies to the outer part of the chip. To make the material more reusable, I decided to have main and detail colors for outer part. First, we round our mask and find the inverses for further use. We apply color to the outer chip itself, and then we take an inverse mask and multiply with an inverse inner mask, which gave us a mask with a no center. Then we lerp our color detail mask and color outer chip using the inverse mask as alpha mask. Finally, we merge the inner and outer parts using the same lerp node, and that by using a full chip mask, we make sure that we don't display any other parts other than the chip itself. To find an emission map, I decided to utilize the normalized cosine idea, however with a different range, from 0.2 to 1. Emission power can be controlled with another introduced parameter. To find an opacity mask, we use our hologram effect and full chip mask. The main material has metallic, specular roughness, and anisotropy levels exposed only for cases when there is no emissive. Otherwise, these introduce details which cannot be seen on a smaller scale. To control if designers want to have an emissive, I came up with an if statement, an exposed parameter that needs to be set to 1. In general, this material has the most reusability in different scenarios and cases, and does not require manipulating a lot of parameters. In this case, I introduced two different chip shapes, round and rectangle, with different details. Both of them have multiple subvariants utilizing different colors. The fourth material is a piece of art. When coming up with this idea, I thought about what is the most prestigious item that intelligent and rich people would appreciate in the casino. One thing that came to my mind, art. However, Cyberpunk is mostly about neon, graffiti, and it does not work well in very rich casino style. Because of that, I started searching different artistic styles such as abstractionism, constructivism, op art, and cubism. While it is possible to describe most of this as aesthetic art, I decided to make a fractal art that's going to be moved over time and is mostly similar to the cubism shape. Fractal itself is implemented as a shader. I came up with a T-fractal and a way to control initial generation, generations to iterate, and the speed of that fractal. Now the hard part. Initially, we want to have some more parameters for generation. First, we split our UV into 1 by 1 square by taking the modular operation. Then, we want to find the smallest distance to any edge of current square. To do that, we take the min of the square coordinate and inverse of that. The smallest distance will be used in calculations of the next generation to determine the scale and the offset. When we look through the generations, find the new smallest distance with a UV split factor and adjust our value of a fractal with the fractal power. Essentially what it does is determining how many splits there are inside one cube by the formula. Finally, we provide an opportunity to inverse the result for different visual effects. Now, when we are done with the fractal part, it's time to discuss the movement. Initially, I tried combining multiple trigonometry functions, however, they did not look very nice. After some research and tests, I decided to implement a golden ratio spiral. First, we calculate the current animation time and have inverse and normalized version of that. Then we do find an angle we should have by translating normalized sine to radians and multiplying by spiral count. We do multiply by spiral count because we want to have twice as big angle in case of two spirals to be done in the same time frame. Later, we determine the rotation direction and find normalized sin and cos values. Moreover, we do find how much distance we traverse in radians by multiplying 2 to represent radians with a spiral count and normalized time. Then, the easiest part, we calculate the golden radius we should have by well-known formula. Finally, calculate the movement by multiplication of the initial radius of the spiral by trigonometry function defining movement of in particular axis, and finally multiplying by the inverse of the golden radius to have constant speed. The last three things are the color and emission. The color is determined by three parameters, either the hue shift speed or the Boolean variable with a custom static color. For emission, we have another Boolean to control the state of it. Finally, I also expose metallic, specular, roughness, and anisotropy values for the possibility of creating different effects with this material such as reflective metallic or matte art. Finally, our last material and most complex one, the aquarium. What might be better than looking at fish in the lounge zone while having a cocktail and lying on the beanbag? However, because of the complexity, I will discuss only the difficult and main aspects of it. First, I created a glass effect by using custom textures of a table and custom reflection vector node. To control the depth of that glass effect, I use channel-specific masking technique. To have correct masking, I need to have a width of the texture. However, there is no way other than to use a custom HLSL node. In the end, we do combine our UV and the glass effect to the get glass UV that's going to be used for every future aquarium item to make it feel that these are inside of the aquarium. The next thing is the aquarium items such as corals and rocks. They do follow the same pattern. You pass the albedo and color mask, specify UV scale, UV shift, and cropping from four sides, clockwise direction, same as HTML margin. For more immersive and realistic behavior, the designer might specify the water flow speed, how strong it will deform the object. Then we pass everything in a function that firstly scales and shifts UV, then crops it by provided parameters. The next step is to apply distortion, which utilizes multi-channel noise texture, mixes the result, and has a power parameter to determine how distorted we want the texture to be. After that, we combine the result with glass UV and use that for getting the color mask and finally coloring the texture using the mask. The point of returning the color mask is to be able to blend multiple objects using the lerp node as it can be seen in the main graph. The last item we are missing in the aquarium is a fish. To make it highly customizable, I provided parameters such as fish speed, movement direction, offset, path time, size, and multiple colors. To create a fish, I have decided to use two HLSL shaders, one for the ellipse body and one for a triangle tail. I'll ignore previously discussed basics such as the shifting UVs or performing mode operations to determine the length of the animation. Drawing the ellipse is pretty straightforward and almost the same as a circle, but instead of radius squared, we do have an x and y squared radiuses. Then we color the ellipse and return it. The triangle tail is a bit more complicated, but the idea is to generalize the code for drawing any polygon. First, we need to calculate the position with rotation using the A10 function and add custom rotation that is converted from degrees to radians beforehand. Then we calculate the angle between each vertex, define the sector number of the position we are at, then snap the position to the closest vertex of the polygon, and finally find the closest vertex distance. Finally, we get our result by performing a smooth step. Finally, we merge the tail and body together and return it to the main aquarium function where it can be merged using the lerp node. Unfortunately, this material is not as highly customizable because to add another aquarium item or another fish, we need to create a whole new subgraph with parameters exposed. However, in the current settings, two corals with two fishes were enough for an aesthetic look. Additionally, it is still possible to adjust these as designer would like with any offsets, positions, or scales.